Okay, we've been working up to this idea of calculating the magnitude and the phase for the Bode plot. And once again, we're talking about a Bode plot being the magnitude ratio and the phase relationship for the input and the output for a whole range of frequencies. But in order to get there, we need to calculate the individual magnitude and phase for a specific frequency. So that's where we're headed today, and to see if we can make some progress on this. I've got some calculations here, and it looks a little scary, honestly. But if we break it down, it's not too bad. And what we start off with here was just our basic definition of our transfer function. We got a transfer function. It's a gain, a numerator, and a denominator. And then we expand that a little bit to have our gain, and then a sum of our zeros divided by the sum of the poles. Okay, nothing new there, nothing surprising. Now, the next is just another form of writing, a way of writing that, just the summation of those rather than having them listed individually. And then this one, we make a slight change in here. As we've been talking, we substitute the j omega in for our s if we want to calculate it at a specific frequency, because j omega on the imaginary axis will give us a pure sinusoidal. And so we put a sinusoidal into the equation at a specific frequency, omega, and then we calculate, and we'll calculate out our g of j omega, and find out what the response of the system is to that inputting, to that specific frequency input. All right, so that's what we need to figure out here, is how to calculate that. Now, the problem with this is that we've got a complex number that we're taking the product of, and then dividing it. And now complex numbers we typically deal with in addition and subtraction. We can do pretty easily with those operations, but the product and the divisor gets a little bit more interesting. And so what we're going to do to accomplish this is we're going to move our complex number into a polar notation, okay? A complex polar notation. So our complex number that we typically think about, a real and imaginary portion, we're moving into this alternate form. And if you look back in your math, you remember there are a couple different alternate forms, and this is one of the alternate forms that we can use to represent a complex number. And in doing that, what we have is our R is just the Pythagorean theorem. Honestly, it's the real portion squared plus the imaginary portion squared, square root, summed and square root of those, and that gives us the R, and then the angle is just the tangent. Now, what we're talking about here is fairly simple. If you think about it, we're just talking about a location here and a vector, and we've got a real portion, sigma, and then in this case, our omega j, and so this length in here is going to be sigma squared plus omega squared square root. And that's going to just Pythagorean theorem. And then our angle in here is going to be the tangent, the arctangent of omega divided by sigma. Okay, so there's nothing really too surprising in there. It's just defining vectors in terms of our geometry in there. And so we've got these. All right, so now if we use these, this r and theta in here, and this alternate form of it, our equation gj omega changes to this form where we've still got our gain, and now we have the poles represented this way, and the zeros represented and the poles represented. Now, we can then split these apart, pulling off the constants, and gathering the e's. And when we multiply the e's together, what we can do is just sum the exponent in there, and the constants collect here as products. All right, so now what we're going to do is we're going to use this portion to calculate the magnitude, and we're going to use this portion to calculate the angle. Okay, so now that looks ugly, and in this form it is, but it actually is not too bad to calculate. And so let me run you through the next through an example in the next lecture, and try to simplify this down to something we can actually do and understand.